Hi, and welcome to Lecture 2 of Psychometrics. In this lecture, we're going to talk about measuring variability and association. These are two descriptive statistics that we really will need a lot later in the semester, so this is a good time to go over the basics. So the plan is as follows. First, we're going to briefly review the concept of variance and standard deviation. This is something that I'm going to assume that you have learned in a previous statistics course, so we'll go over it pretty quickly. The new material for today will be to talk a little bit more in depth about the concept of correlation. And particularly, we're going to talk about how to compute four different types of correlation or measures of association. And they are the Pearson correlation, the phi coefficient, the point biserial correlation, and then finally, the Spearmint correlation. Specifically, we'll talk about how to compute them and importantly, the situations in which you would compute each of them. Okay, so let's begin with a review of what we mean by measuring variability. So when we talk about variability of data, what we are asking is how much on average does each number in the data set differ from the most typical value, usually the mean in this case. So to illustrate, let's walk through a very simple example. So let's suppose we have 5 data points listed here in a column, 2, 3, 5, 8, and 12. You can easily find that the mean of these 5 data points is 6. So if we want to know how much on average each number differs from that typical value 6, we can simply measure the deviations. That is, we take each data point and subtract the mean. So that's what we get in this second column. If we take 2 minus 6, we get -4, 3 minus 6, we get -3, and so on. Now what happens in this case, if we scroll down a little bit, is we say, okay, on average, how much do these numbers differ? Another way of asking that is how is on average, what's this deviation? So we can add those together and divide by 5 to find the average deviation. And what happens is that average deviation turns out to be 0. In fact, when you add these 5 numbers, their sum is 0. So no matter what you divide by, the average is still 0. So that's not helpful at all. So how do we circumvent this problem? The typical way that we do so is instead of considering the raw deviation scores along with their signs, we simply make each of those deviations positive. We do that by squaring the deviations. So we take each of those deviation scores and we square them. So -4 squared would be 16, -3 squared would be 9, and so on. Now we can find the average of these squared deviations. If we do that, we simply take the sum of those squared deviations, divide by the number that we have, which is 5. That turns out to be a sum of 66 divided by 5, which gives us an average squared deviation of 13.2. And this number, 13.2, is defined as the variance. Okay, so that's our review. We define variance as the average of the squared deviations. You can write this down in a formula if you would like. It's simply the sum of each data point minus the mean, that's the deviation, squared. Right? So we square them, add them up, and then we divide by n. Now the problem with variance in your statistics class is that variance is on a different scale from the rest of the data, right? The variance we got was 13.2. That's on a different scale. That doesn't tell you on average how much each of these points differs from 6. It's a square deviation, not a raw deviation. So to fix that, we often take the square root of that variance and we call that the standard deviation. And so there's the formula. Again, you just compute the variance as the average square deviation and then you take the square root to get the standard deviation. Now there's some notation that we're going to be using a lot this semester, but before that, let's just mention here that if we take that data set that we started with, the standard deviation is the square root of the variance. Well, we found the variance to be 13.2. So if we take that square root, that gives us a standard deviation of 3.63. Okay, so that tells you on average, roughly speaking, on average, each data point differs from the mean by about 3.63 units. Now, a quick word about notation. Standard deviation is typically written with the Greek letter sigma. That's a lowercase sigma. And thus, variance will be written as sigma squared, thus expressing the relationship between standard deviation and variance. Variance is simply standard deviation squared. So we'll see that notation quite a lot this semester. So I want you to get used to it. Okay, so that's how we measure variability. Variance turns out to be actually the more important of these two concepts, and we'll begin to see that in the next lecture. So I don't want to get ahead of myself right now, but that's what we will be getting toward. So now I want to move into the main part of this lecture, which is to talk about measuring association. When we talk about measuring association, what we're doing is we're saying consider two sets of scores. They might be scores on some test or two items within a test, but just two sets of scores. And we want to ask, to what degree are those sets of scores associated with each other? Another way to say that is, to what extent do they co-vary? Right? So we can talk about how they vary with each other, or how they vary within each data set. That's the variance. Is there a way to talk about their covariance? And the answer is absolutely there is. In fact, we can define a formula that looks very similar to what we did with variance. To define covariance, we simply do this. We take the sum of the deviations of the x's from the mean of the x's times the deviation of the y's from the mean of the y's. So it's like each of these columns here, we're going to compute deviation scores, and then we're going to just multiply those deviation scores together. When we multiply them together, we'll add them up, and then we'll divide by n. So it's like the average cross product of the deviation scores. That average is called covariance, and its symbol is sigma xy. Okay? So that's our covariance. We're going to actually talk about how to compute covariance now using the data set that you see in front of you. So what I've put down here are two rather arbitrary sets of data. I'm calling one of the variables x and the other one y. You can see the x is in the left-hand column. I've already gone to the liberty of computing the mean and standard deviation of each of those. So the mean of this x data set is 4, and the standard deviation turns out to be 1.41. You compute it using exactly the same techniques that we just reviewed a few minutes ago. For y, we get the same mean. Y bar equals 4. Standard deviation is a little greater here. It's 1.79. Now my goal is to compute the covariance. So to compute covariance, we look at this formula and try to unpack it. What it's asking us to do is find the deviation scores. xi minus x bar is simply, what do you get when you take 6 minus 4, 2 minus 4, 5 minus 4, etc. So I've gone ahead and written this in this first column here. If we do those deviation scores, 6 minus 4 is 2. 2 minus the mean 4 is negative 2. 5 minus 4 is 1, etc. Okay, so those are the deviation scores for the x's. We're going to multiply those by the deviation scores for the y's. So we need to take each of these y values and subtract the mean 4. So we do that here. Similar to the x column, if we take 6 minus 4, we get 2, 2. This one's a little different. 6 minus 4 gives us a 2 here. 4 minus 4 gives us 0, etc. So these are the two deviation scores. Now the covariance is the average of their products. So that means we need to multiply the deviation scores together. Okay, so this x minus x bar times y minus y bar is going to give us 2 times 2, which is 4. Negative 2 times negative 2, which is 4. 1 times 2, which is 2. And then each of these will end up with a product of 0 because there's a 0 in the two terms of the product. Okay. So we're almost there. The covariance is you take these products and you add them up and divide by the number of products you have. In other words, you find the average of them. So we'll do that here. That sum, if we add up these products, is 10. 4 plus 4 plus 2. And then if we take 1/5 times 10, or simply 10 divided by 5, we get a covariance of 2. Okay. So covariance here is 2. Okay. So this tells us a little bit about how they covary. But there's a much more common way of indexing how they covary, and that's to take this covariance and scale it. Just like we took variance and scaled it, we're going to take covariance and scale it to something that's a bit more interpretable across multiple sets. And that concept is called the Pearson correlation. So from this covariance, we can easily define the Pearson correlation, which you've probably heard of before, but this is how it's defined. You take the covariance that you just found, and then you divide by the product of the two standard deviations. Okay, so we had a covariance of 2 up here to find the correlation, or the Pearson correlation technically. We're going to take that 2 and we're going to divide by 1.41 times 1.79. Okay, let's see that worked out. It's going to look like this. Covariance divided by the standard deviation of x times the standard deviation of y, and that gives us a correlation, a Pearson correlation of 0.79. The symbol for correlation is R, and that's the value. Now, a couple of facts about R. These are things you might know already, but serve as a good review. R is fixed to be on a fixed range. It is never less than -1, and it's never bigger than 1. So it's always between those two numbers. And the closer you get to these endpoints, 1 or -1, the degree of association increases. So it's like they are much more in line with each other, much more associated with each other. The worst you can do is a correlation of 0. That means there's absolutely no association between the two variables. Okay, so with this one, if we wanted to interpret that, that's a pretty strong correlation. Okay, you might remember from maybe some statistics courses or papers that you've read that you can scale these in certain ways. There's various recommendations that different authors make. I'm not going to teach those specifically, but a correlation of 0.8 is a pretty good correlation. So you can always Google what's a big correlation, and you'll get some benchmarks for this. I'm not too interested in specifically calling this medium, large, whatever. It's pretty big. Okay, the closer you are to 1, the more associated the two variables are. And let's leave it at that. The closer to 0, the worse associated they are. So this is the Pearson correlation. Now, you can go through life just computing Pearson correlations, but technically you may not be computing the right correlation. The reason is because the Pearson correlation always assumes that both of your variables x and y are continuously scaled variables. That is, they are on an interval or ratio scale. They reflect things that can be divided into smaller and smaller intervals. They're not just whole numbers. They're not just Likert scaled items. They're like measurements that you would get from a continuous measuring instrument, like a ruler or a graduated cylinder, or response times in a behavioral task, those kinds of things. So the question, of course, would be, what if this is not the case? What if your data, which by the way it is often when we're talking about tests and measurements and psychometrics in general, what if they are not continuously scaled variables? So the rest of this lecture, we're going to talk about 3 cases that we can deal with and compute a measure of association when one or both of those variables is not continuous. Okay. So the first of these, let's find the right spot to delete here. The first of these is called the phi coefficient. Okay. If you want to call that phi, please don't. It's called phi. The Greek letter is pronounced phi. And the phi coefficient, as you'll find out, is what you use when both x and y are what are called dichotomous variables. That is, they only have 2 options, 0 or 1, or yes or no, or anything that can be broken into 2 categories. We can use this phi coefficient. The second example is something called the point biserial correlation. And this is one that we can use when one of the variables, let's say x, is dichotomous, whereas the other one is continuous. Okay, so it's kind of a halfway in between Pearson and phi. And then the last one that we'll talk about is when you have ordinal variables, you'll use something called the Spearmint correlation. And we'll talk about how to deal with that case momentarily. Okay, so let's first talk about the phi coefficient. Now, as we just mentioned above, let me get a little bit more space here. As we just mentioned above, the phi coefficient is appropriate when you have pairs of dichotomously scaled variables, that is, yes or no variables. So as an example, let's consider 2 test items. So you got a test and it's got multiple items on it. Let's just consider 2 of those. We want to see if their answers are associated with each other. But the problem is those 2 test items are only scored as correct or incorrect. The only data you can glean is a 1 or a 0, right? 2 possible options. So the way we might take data that look like that is we might put them into a contingency table. We might say, okay, so for the x variables, they could either be scored 0 or 1. The y variables, they could either be scored 0 or 1. And that means there's 4 options for the associations. Both could be 0, so there were 8 people who scored a 0 on both x and y. There could be a 0 with a 1, a 0 with the x and a 1 with the y. There were 4 people that had that pattern. There could be a 0 with y and a 1 with x. There were 12 people that had that pattern. And then finally, there could be people who got both y and x correct. And there were 16 people who had that pattern. Okay, so that's what we're going to do. We're going to figure out how to find the correlation of x and y from these minimal data. How do we do it? Well, this is the phi coefficient. The phi coefficient uses just the information that you can get from this table to give a nice get a nice measure of association. And here's how it works. Might look a little bit scary. So let's talk about what this is. This is the notation for phi. It's a Greek letter. I use that notation. Sometimes you'll see phi look a little bit like this. Okay. My history in mathematics has long since taught me to write phi just like you have it written right there. You can do it either way. So if you want to compute phi between x and y, we do this. It's pxy minus px times py over the square root of some stuff involving px and py. What is all this stuff? Well, there's 3 things here we need to know. Pxy is simply a notation to represent the proportion of people who scored a 1 on both x and y. So that's these 16 people here, right? But it's expressed as a proportion. Okay, so 16 out of how many total? We'll figure that out in just a second. Px is similar, but this is the proportion scoring 1 just on x. So it ignores y. Okay, it kind of collapses across y. What's the proportion who scored 1 on x? Again, we'll figure that out in just a moment. And then similarly, py is the proportion scoring a 1 on y. Okay, so let's copy this table down and let's see if we can figure out how to work this. So as I said, we're going to have to kind of figure out what the totals are. So I'm going to do this 2 ways. Get a red pen here to do this. The first thing that I'm going to do is I'm going to work down the columns. I'm going to find my total x's who got a 0 and my total x's who got a 1. So to do that, I'll take 8 plus 4 in this column, and I'll get a total of 12 people who put a 0 on x. And then similarly in this column, I'll take 12 plus 16, and I'll get 28. It's a total of 28 people who scored a 1 on x. We'll do the same thing for the y variable. How many people scored a 0? Well, 8 plus 12, which is 20. And how many scored a 1? 4 plus 16, which is also 20. Now, the nice thing about doing it this way is either way, if you add these 2 marginal totals or these 2 marginal totals, you get a total number of responses of 40. That is, all 4 of these cells add up to a total of 40 responses. So from those 40 responses, we can now compute the proportions that we need to compute the phi coefficient. We need these 3 right here, pxy, px, and py. Let's start with the top, pxy. Pxy, remember, is the proportion of people who scored a 1 on both x and y. You can think of it as both got both x and y correct. Okay? Now that's these 16 people right here. Okay? That's 16 out of 40. So we need to express 16 out of 40 as a fraction. And if we do that, that turns out to be, let's see, that's 4 over 10, that's 0.4. Okay. So that's pxy as 0.4. Again, has to be written as a proportion to work here. Now we can do the same thing for px, the proportion of people who got x correct or scored a 1 on x. So if we just look down here at the x totals, again, circle those, 28 of them got it correct, so that's 28 out of 40. It's 28 out of 40. If we simplify that, let's see, that's 7 out of 10, which is 0.7. And then finally, py, it's actually pretty easy. What is the proportion of people who got y correct, that is scored a 1? That's 20 out of 40, which is 0.5. So once we have those 3 proportions, we can now easily compute phi. So just rewrite the formula just so we have it in front of us. And we just now need to keep track of all the numbers that we just figured out and do the arithmetic. So we'll start off by replacing every one of these proportions with the values that we got just above. So we put the 0.4 here, and the 0.7 for px here, and the 0.5 for px here. And then down here in the square root, I've got px is 0.7. 1 minus px, that's kind of like the proportion that got it wrong, so that's going to be 0.3. These two will always add up to 1. Okay, and then similarly down here, the py was 0.5, and so the 1 minus py is 0.5. So what we need to do is just be real careful with the arithmetic. We need to multiply those, which gives us 0.35, and then subtract that from 0.4, and then we need to multiply all that together and take its square root and then divide. So if we do that, we get a top of 0.05, a bottom of 0.229, and when we find that quotient, it gives us, to 2 decimal places, a phi coefficient of 0.22. So this is a positive relationship. So as scores on X increase, so do Y. It's a pretty small one. Okay, anything down in the 0.3 or below is a pretty small correlation. But that's it. That's what the phi coefficient is. It's interpreted exactly the same as the Pearson correlation. It's just a different type of correlation for specific types of data. Okay. A couple of facts about phi before we move on. First fact is, just as I mentioned, the phi coefficient is interpreted exactly the same as the Pearson correlation. But one thing that I'll mention is just a technical point that might come up at some point later in the course. The range of the Pearson correlation is -1 to 1. That's not always the case for the phi coefficient. The range will actually be reduced when px is not equal to py. What that would mean is that the proportion of people who got X right is different from the proportion of people who got Y right. Interpreted in terms of tests and measurements, that means that the item difficulties are different. So if the item difficulties are not equivalent, then we get a reduction in range of the phi coefficient. And we'll talk about how to deal with that again later in the course. But this will get you a little bit familiar with it. So when you have 2 dichotomous variables, basically all you can do is construct a contingency table like this. That's how you turn a contingency table into a correlation. It's the phi coefficient. What about if you have one of the variables that's dichotomous, but the other is continuous? Well, this is where the point biserial correlation comes in. So here's an example that meets this categorization. X is a dichotomous variable. You can see X either is a 0 or a 1. Okay? But Y is an item that has all kinds of numbers on it. These are all whole numbers. We're going to just assume that this is a continuous scaled measurement. Okay, but it could also have decimals and it would be fine. And we want to know to what extent are X and Y associated with each other. Is there a correlation between them? So we do this with the point biserial correlation. And oops, I went a little too far. Let me go back under here. Here's how the point biserial formula works. So there's a lot of formulas this time. You just want to write them down so that you can use them. The point biserial formula looks like this. Let me scroll up just a little bit here. Okay. So the symbol that we'll use to denote the point biserial correlation is this R with a little PBIS, point biserial, as a subscript. This is to keep it separate from R, which is the Pearson correlation. The formula looks like this. It looks like a z-score almost. It's not quite, but you take something called y1 bar minus y bar over sigma y, which is just the standard deviation. And then you multiply that by the square root of px over 1 minus px. Oops, once again, we're a little bit too far there. Okay, so what are these? We should talk about these real quickly before I hide all that. So three of these we know already. Y bar is just the mean of the y's. So we just simply take across those y scores and add them up and divide by, I think there's 10 in this case. Sigma y, that's the standard deviation of the y. So you can, take their square deviations, add them up, divide by 10, take the square root. Okay. What is y1? That's a little bit new for us. This y1 bar, this is the mean of the y's which the x variable associated was correct or scored a 1 on. That's what the subscript 1 represents. So let me say that again. It's the mean of the y's for which the associated x variable was scored correctly. So for this one, let me get a little red mark here. That's going to be these scores right here. Okay, that we're going to take the mean of those, and that's going to be that y1 bar. Okay, so it's a smaller set. It's only 6 of them, and it's going to be, of course, conceivably different from y bar, which is why we measure the difference between them. And I didn't mention this, but px is the proportion of people who scored x correctly. That has got a 1 on it. In this case, that's 6 out of 10, which is 60% or 0.6. Okay, so from all this, using those definitions, we can compute the following. It turns out that y1 bar is 6.67. Again, if I just find the mean of that red circle there. Y bar is 5. Sigma y turns out to be 2.76. And as we just mentioned, px is 0.6. So again, these are all things you have to compute, and you don't just know them. All right, so there's some work that goes on, but you can compute them pretty easily. Once you have those values, then we can compute the point biserial correlation using the formula. So the point biserial correlation, we put in y1 bar is 6.67, y bar is 5, standard deviation of y is 2.76, and then we multiply by the square root of 0.6 over 1 minus 0.6, which is 0.4. Again, be careful with your arithmetic here. Let's see. What I like to do, guys, is when we have a lot of stuff going on here, I'll keep more decimal places than I need at the end. So in this case, I'm going to give 3 decimal places to each of these 2 pieces of the product. So that first one simplifies to 0.605, and the second one simplifies to 1.225. And then if I multiply those together, I can round that final answer to 2 decimal places, and it gives me 0.74. So that's the correlation. Again, it is interpreted exactly the same as a Pearson correlation. Closer to 1, the better the fit. This is a pretty high degree of association. Okay, and it's a positive association. So as x goes up, so does y. You can actually see that in these data up here. As x goes up, that means as people get things correct. Notice those scores are higher than these down here. So that's what that correlation of 0.74 is telling you. Okay, it's measuring the degree to which that pattern is there. A couple of facts about the point biserial correlation. Just like with the phi coefficient, the range from -1 to 1 is reduced, and it's reduced whenever px is not equal to 0.5. So if you have something that does not vary at a 50% probability, in other words, people get more than 50% correct or less than 50% correct, your range gets reduced. You can only get a maximum less than 1 or greater than -1. And I'll say this, the value is absolutely identical to what you would get if you computed a Pearson correlation, but it is slightly easier to compute. Okay, so that's one of the reasons that the point biserial formula exists, because this process is a lot easier in general than doing the Pearson correlation, especially if you have big data sets. Okay, so that's the point biserial formula. The last one that we'll talk about today is the Spearmint correlation. The Spearmint correlation is used in a very specific case, and that's when you have ordinal variables. And it's when x or y is ordinal. So if you have one or both that are on an ordinal scale, that is, they only denote order, but they don't denote magnitude difference between them. A perfect example of this is Likert scale, which we use a lot in psychology. So anytime you have Likert scaled items, you should be using a Spearmint correlation. Now the reason will become apparent when we see how the Spearmint correlation works. So let's look at an example. Here's just another example to throw up here. Here are 2 variables with scores. These are Likert scaled scores. I've actually written these on a scale of 1 to 7. You can think like 1 is strongly disagree, 7 is strongly agree. Then the things in between represent a graded adjustment of that. So what do we do here? Well, let's talk about what we do first. Well, this is a fun formula because who knows what all this is, right? The Spearmint formula works like this. We're going to call it RS for Spearmint, and it's 1 minus 6 times the sum of di squared over n cubed minus n. Okay, what is all that? Well, n, I think you can figure, is the number of pairs. Okay, so this is going to be 5 in this case. I've got 1, 2, 3, all the way to 5 pairs to consider. But what is di? Well, this is something new for us. Di is the difference in ranks for the ith pair. So that's what makes this correlation very different from the previous ones. Since it's an ordinal scale, you can't really talk about mean because there's no magnitude here. It's just things are in order. We know 1 is less than 7, but we don't know how much less it is. So what we do is we compute for each of these data points that we see, each of these scores, how does it rank in the data set? And we'll see exactly how to compute that in just a second. We do that the same thing for the y, and then we multiply those ranks together we take the difference in those ranks and then we square them. And then we add them up and then we do some more stuff. Okay. So let's talk first about how to compute the DIs, the difference in ranks. So we'll go down here. I've just copied the table again, just to help us out a little bit. So how do we talk about ranks? Well, let's talk about it and then show it. You can order these however you want. We're going to go with bigger number is the first ranked. Okay, so we're going to rank this in terms of highest. So if we go down this list by X, this would have a rank of 1, right? Because it's the highest score in that data set. Now, the next highest score would be this one, the 5 down here. So it would have a rank of 2. Then the next highest would be this one, which would have a rank of 3, and then 4, and then 5. Let's show what all that looks like. Okay. So you can see here, these are the ranks for X. Again, highest is the first ranked. We'll do the same thing for Y. Let's talk it through and then show it. The first ranked would be this one. It's the highest. The second rank would be this one. The third ranked one would be this one. The fourth, next highest, would be this one. And then finally, the fifth ranked would be this one. So there we go. Now what we're going to do is the DI computation. That's the difference in ranks. So when you take a difference, you have to pay attention to order. It really doesn't matter because we're going to be squaring it in just a moment. But let's just say that we're going to take the rank of X minus the rank of Y. Okay. So when we do that, the rank of X, 1, minus the rank of Y, that's a difference of -4, 1 minus 5. The next pair would be 5 minus 4, or 1. The next pair would be 4 minus 2, or 2, etc. Let's show that. Okay. So here are the DIs, the differences in ranks. And then because some are negative, some are positive, we're going to square them to make them all positive. So that gives us these squares, 16, 1, 4, 1, and 0. And then we're going to need to add those up. We're going to need to find the sum of those squared ranks. If we do that, we get 16 plus 4 is 20 plus 2 is 22. So now we're ready to compute the Spearmint correlation. So let's write down our formula again. This is, again, 1 minus 6 times the sum of the squared differences in ranks divided by n cubed minus n. Let's plug all that stuff in. Okay. So 6 times, we found that sum of rank differences as 22. And then n is 5. This is the number of pairs you have. So this will be 5 cubed minus 5. That's 120. So this simplifies to be 1 minus 132 over 120. And if we do that arithmetic, we get a negative 0.10. So that tells us that there's a slight negative relationship, very small one because the magnitude is pretty close to 0, but the sign tells us it's a negative relationship. As one goes up, the other goes down. So that's that. That's the Spearmint correlation. And notice it uses nowhere does it use the mean or standard deviation. That's because they're ordinal variables. This is an example of what's called non-parametric statistics, and there are whole books written on it. This gives you a little taste. So that's it for this lecture. We've done a lot, but mostly we have focused on measures of association. We've talked about the Pearson correlation, which is just the covariance divided by the standard deviations. We've talked about the phi coefficient, which is how you measure correlation for dichotomously scored variables. We've talked about the point biserial correlation, which is when you have one dichotomous with one continuous. And then finally, when you have ordinal variables, you can use this Spearmint correlation. It doesn't have to use the mean, you just use ranks. So that's it. I hope you had fun with that, and I will see you on the next lecture.